Hey, so I'd love to be as cool as Natalie Tran and say that you're seeing me in stick figure form because my camera broke over the weekend. But what actually happened is that I went to a salon in London and now my face looks, well, like this. So there's that. So the sounds entering your ears from this video are the result of oscillations from your computer speakers producing sound waves. Similarly, the image you're watching on the screen is in simplest terms visible light waves. And these two waves are great examples of both transverse and longitudinal waves. In the case of sound, these waves are longitudinal waves. This means that the oscillation movement is parallel to the direction of the wave propagation. So when particles are moved left and right in an oscillation or vibration, this in turn creates a wave. Think of a slinky, stretched out where there are even intervals between the spring coils. Now, when we start to move one end, this left to right movement creates a wave, and the waves pass through the slinky, but the slinky itself does not move anywhere. Now, you've probably noticed that as the oscillations move through the spring, there are compressed areas where there is no or very little room between the spring coils. This is known as compression, and as it's a longitudinal wave, there must be areas where the spring coils are spaced either side of the compression, and this is known as rarefaction. Importantly, longitudinal waves require a medium like water, rock, or air to travel through. Without this, they cannot be produced, and that is why in space no one can hear you scream. Moving on to light, light is an example of a transverse wave. A transverse wave is one where the direction of the wave is at a right angle to the direction of propagation. Transverse waves can be represented in the classical sinusoidal wave. An example of a transverse wave would be a water wave, where a disturbance on the water surface creates a wave. And just like a transverse wave, it is only the transfer of energy propagating in the direction of the traveling wave. There is no mass transport of particles. Now, unlike a longitudinal wave, some transverse waves don't require a medium to travel through, like light. Light waves can travel through a vacuum, so whilst no one can hear you scream in space, they can definitely see you. So there are two types of waves, and although different, they share the same parts of a wave that allows us to examine waves. So let's have a look at that. So a transverse wave kind of looks like this, and a longitudinal wave kind of looks like this. Now you might think that they look nothing alike, but transverse waves are often represented as longitudinal waves to help us better understand them. So let's take a look at the classic longitudinal wave. Let's start with the peaks. This is the highest point of the wave above the rest position. This is followed by the trough, or the lowest part of the wave. The distance between a peak and a peak, or a trough and a trough, is called a wavelength. The amplitude of the wave is the maximum displacement from the rest point. Now, as waves propagate, there will be a certain number of waves passing a point each second, and this is known as the frequency. The unit of frequency is, as you probably already know, hertz. And lastly, the period is the time it takes one wave to pass a point. Now, depending on the wave, it will have a very specific fingerprint. Longitudinal waves, like sound waves that the human ear can pick up, typically have a frequency between 20 and 20,000 hertz. Anything above 20,000 hertz is known as ultrasound. Now, with sounds, the higher the amplitude, the louder the sound, and the lower the amplitude, the quieter the sound. And when traveling through air, sound has a speed of approximately 330 meters per second, and while 20,000 hertz traveling at 330 meters per second seems a lot, it's nothing compared to waves on the electromagnetic spectrum. Electromagnetic waves transfer energy as radiation from source to the absorber. They can travel through a vacuum and air at the same speed. The electromagnetic spectrum can be split into 7 distinct, although continuous categories, from radio waves that have a very long wavelength, low frequency and low energy, to gamma rays that have a very short wavelength, high frequency and high energy. The 7 categories are split into radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. And the speed of electromagnetic waves? Well, they travel at 300 million meters a second, or the speed of light. And we know all this about the electromagnetic spectrum because Heinrich Hertz demonstrated the existence of electromagnetic waves predicted by James Clerk Maxwell. In 1865, Maxwell had theorized that electromagnetic fields travel through space at the speed of light, and that light is similar, consisting of vibrations of the same medium just at a different frequency. Although widely accepted, experimentation was lacking until 1887 when Hertz built apparatus to confirm Maxwell's theory of wave propagation. This video was sponsored by Brilliant. Every day, Brilliant publishes several daily problems that provide a quick and fascinating view into math, logic, science, engineering, or computer science. As an example, in the past month, tens of thousands of people have used computer science to efficiently bake cheese biscuits. Whether you're stuck in a commute or you just want to learn something new every day, Brilliant's daily problems are a fun, bite-sized way to master concepts by applying them. Each problem comes with illustrations, animations, or interactive visualizations, and all the context you need to solve the problem yourself. If you like the problem and want to learn more, there's a related course that explores the same concept in greater detail. So if you want to actively learn new fascinating concepts each day, head over to brilliant.org/sciencewithkatie and finish your day a little bit smarter. The first 200 of you to do so will get 20% off the annual premium subscription, so you can view all the daily problems in the archives and unlock their dozens of problem-solving courses. And that's it. If you like this video, give it a thumbs up. If you want to see more, hit subscribe. And a big thank you to my patrons on Patreon, and thank you for watching. Bye!